And I will share my screen. Then my chat's working again. Okay, I'm gonna move some stuff around here. And just before we get going, I want to be sure that you guys can hear me. Yep, test. You can hear me and you can see my screen, everybody. Good. Yes. Nick, you all set, Nicholas? Yes. All right, here we go. Moving on. Week 11, timers and counters. The timers and counters of this aren't actually bad. It's the crosstalk activity at the end that might get you. So I encourage you to take a look at the lab, especially the last one, and be sure you're ready to go on the lab next time. You have a lecture that's going to be recorded. You're going to fill out your worksheet here and get that into me. We're going to be talking a little bit about scheduling. Describe the difference between task programs and routines, give examples of periodic tasks, difference between local and global tags. We're going to go over this again. Explain how the retentive nature of subroutines can create problems. Describe how asynchronous scan and Siemens timers provide functionality. So we're talking about how the Siemens is a different scan pattern than the ARS logic. Describe the purpose of interlocks between controllers. That's what the lab is about. You want to read it and describe what functions of a relay. That's what we're working on. But before we do that, we'll do our function block review. The function block went okay, some better than others. Once again, I think it's a matter of, coming to class, kind of being prepared to know what you're going to get into because it's a little bit different. And we talked that functions and function blocks are subroutines. They're similar to subroutines. They're a program within a program. In order for that program to run, it has to be called, and the terminology we use is scheduled. Okay, it has to be scheduled. Function blocks and subroutines need to be scheduled. And you just can't copy and paste them. That's what some people were getting in trouble with. They were coming in here and they put this is not a function block, but I'll just throw it here. They had made their function block, they called it something, they put it here, and they just went copy, and then they went here and they went paste, and that didn't work because when you schedule a function block, you get a data block. So it needs to be truly scheduled, not just copied and pasted, okay? And so that worked out. We'll do a little bit more of that later when you get the data block over here. We'll be looking at it just a little bit more. They're basically a way to organize your code. You can box up a bunch of code inside of the subroutine, and then you can schedule it over and over and over again. It's similar to, somebody pointed out, kind of an add-on instruction as well. Functions and function blocks are just a way to reuse that code with different inputs and outputs. And we'll talk about whether we're using local or global tags, right? So functions do not have memory. And that was the first ones we did with a function. You could reuse the code, but I had you look in there when it was running, and you could saw that there's no data block, and therefore at the beginning of the scan, it zeroes everything out, and then there's nothing to remember, and so it just then solves the ladder logic, updates the outputs, and then zeroes everything out, so it doesn't remember the prior outputs. Function blocks have memory, and they have a data block created once the function block is scheduled. So scale of 1 to 10. Does everybody agree with this? Function blocks, no data block, no memory. Function blocks, memory. And everybody saw that. Everybody seeing that? Just Corey, anybody else? All right. Another thing, the issue is people were coming up with a function block, and you came here, program blocks. I'll just do it. Add new block, and I'm going to call it test. It's going to be a function block. Okay. And then I want to schedule it into the main. So I'm here in the main. And if I want to schedule it, I bring it into here. And it says, do I want to create a data block? Yes, I do. Okay, there it is. So now this function block says test DB. And then here's test DB. Here's the function block. If I schedule this again, and I could do it on a different network, or I could just do it in this network here. I'll do it again right here. Schedule it again. Let's say it had some code in it. I don't know. It comes in there, right? Now, this is test DB1. That's the data block. And there's the test DB1 data block. So if I come into here and I delete this, notice that it didn't delete the data block. The data block is still there. That data block is now associated with nothing. You're starting to create garbage here in your program because people were doing this and modifying this and deleting it, and then they were getting data blocks, and they had all this stuff going on over here. And then you were then referencing information either in your data blocks or in your function blocks that no longer existed because it didn't, you deleted it. So what you got to be careful is that the function block is associated with the data block. And so if you don't need this, then, you know, I guess you can delete it, but you get too much going on and you've got just a big mess going on. Okay. So how about that? That scale 1 to 10 makes sense. Sometimes it's better to start over, you know, because you get crap going on and you can't figure out what's going on. And a lot of people were struggling with this, and it's going to get uglier as we get going here. Okay. If I come into this test right here, by the way, let's go into test. That's my function block right here. You know, this slides up and down to allow me to look at, you know, what's going on. But if I wanted to add, you know, a local tag such as input right there, okay, I added a local tag. Notice I didn't do any ladder logic here, but I go back to my main. Notice it's red because I've changed the tags, the internal tags inside of here. And then if I, you know, right click this, what I got to do is do an update block call, because it does want me to update that. Yes, I do. Okay. I noticed there's my local tag. It just came in as an input. And what we've been doing up to this point is I got some tags made here. You know, I got PB start, you know, PB. We've been associating the global tags out here in the internal tags, you know, in here. Okay. So if it's red, you got to update the block call. And if you've used this more than once, you'll have to update. You have to update the block call on all of them. And that's what we do. We do use them more than once. That's the purpose of the function block. FC and FB can have local internal tags. Functions and function blocks can have internal tags that are not associated with a contact bit or coil, which would be I, Q's, or M's. You know, these are my internal tags. You can have them. Global tags are associated with a contact, a bit, or a coil. So if you have an I's, Q's, or M's, those are globally scoped tags. Okay. Now, the global tags can be used in the function blocks if you want. You can do that. Okay. If I come here and I wanted to go inside a test here, let me look inside a test. That's my item here. And I'm going to just drag a couple of contacts in here, and I'm going to drag one in here. Okay. So I can use, and this is a ladder logic inside of my function block. I can use a my local tag here, input. Okay, input. I can use, and a lot of times we do use the input. Or inside of here, I could use a global tag. Here's a PB stop. That's an actual I 0.0. That's that. Okay. And then I'll put an output here. By the way, output, I just call it out. That's fine. I can just drag it here too as well. There's a lot of ways to skin a cat here. So I could use global tags inside of a function block. But what about this tag input right here? That's a local tag. Well, if I go to my main and I want to put a tag here, you know, notice that tag doesn't exist. I can't use that globally out here because that tag only exists inside of here. And notice I changed something, so I do need to update the block call there to get it to look like this. All right. So internal and your internal local tags or your external global tags. Local tags cannot be used in the main OB, only your global tag. So we're going to keep talking about this. How you feel on a scale of 1 to 10 about the local, internal versus the global tags? Yep. Starting to see a little bit. Okay. Yep. And then we'll go over a few other different ways to program this if you want. Okay. So a function or a function block which has internal tags will display those tags once scheduled. So I schedule it, and here they are. Run PB, forward, reverse switch, run jog, auxiliary, safety. These are internal, and they're inside of the rectangle. global tags can be assigned to these tags. So run jog. When this global tag, which is input 0, 0, I would expect to see a toggle switch on your wired into your system here. And here I expect to see a push button wired into there. And when you push the button, it then comes in here and it's going to change the state of this internal tag. And remember, I can schedule this a bunch of times and get a bunch of tags called run PB. But these run PBs are internal. The function blocks don't see each other. So just because this run PB internal tag is true, it doesn't mean it's true anywhere else. The global tag run PB I0.1, well, when that gets true, it's going to be true everywhere that is, because there's only going to be one of them. Okay. Subroutines, function blocks, functions can be conditionally or unconditionally scheduled. We talked about that. So I got a function block here. This is unconditionally scheduled. I could conditionally schedule it if I want, like I'd have to make a selector switch and allow this to work or not. But a lot of times, mostly, you're just going to see them unconditionally scheduled, and that they will just run. Okay. Sometimes it's useful to interlock the conditional call of a function block if an output is used more than once. I don't really recommend using an output more than once, but you could, call something. If some reason in here you had, 2 of these and you were using an output, more than once. Oh, so let's undo that. Drag the wrong one there. Sorry. I'll put test in here. Let's do this. Sometimes you might schedule this like that and then schedule this close like that. And so if this was I don't know if I got a PB, what do I got here? I got start, stops. I'll just use stop, whatever that is. I'll use the same button here. Stop, PB stop, but a lot of times it would be a selector switch. So these are the same tag. So when this is true, this is false. When this is true, this is false. So if you conditionally schedule these and you just use the opposite of them, well then, if this one's running, this one's not. And if this one's being called, this one's not. So that concept here of using the same selector switch, open and close, to schedule one and unschedule the other, or schedule that one and unschedule the other one. Does that make sense here? Scale of 1 to 10. How about conditional scheduling? And we've done a lot of that. Schedule this and not schedule that, or call this and not call that. Anybody else? Yeah, you guys seeing it? Wonderful. Okay, here we go. Sometimes it's useful. It's better to use internal bits instead of using an output twice. So if you want, and I'll go over this, if you want to don't use an output twice. You could use an internal bit. And we talked about, having like a run bit and a jog bit in parallel to turn on an output or turn on a motor starter. Instead of turning on the motor starter in one condition where you're in run, and then turning on the same motor starter in another condition when you're in jog. Is it running or is it jogging? You've used the output more than once, use a bit. Sometimes it's helpful to keep outputs in the main OB, but not always. I got some run jog examples here. So here we go. These are functions. They could be function blocks, either one. But I got run jog. Look, this is a selector switch. So if this is true, this is false. If this is true, this is false. I'm switching between them. I'm either running or I'm jogging, right? And so if I'm running inside of here, I hit the start button, the motor comes on. And if that would be if the jog was true and it was called. And if this was true, then this would be false. So therefore, I'd used an output more than once. But it can only be true either in this case, because that's true and this one's false, or in this case, when this is true and that's false. So I used a motor output more than once. Probably not a great idea here. And notice that this should probably, if I'm doing run, this should probably be a function block so that it would have a memory. But that's what we were learning, function blocks with memories. But the way that I did this will work, because inside of these functions, I used global tags. And therefore, I don't need to be worried about the memory in this case, because the global tags are going to be managed outside of the function blocks. So notice I have the I's and the Q's internal to here. And so once again, if I schedule this, start, stop, motor, this one would run. And then this one would. Now, so far, this just makes it. Does this make sense? That I've got two subroutines, and I've used global tags in them, and I've used the output more than once. I've used it in here once, and I've used it in here once. You know, probably not a good thing. Is this making sense to you guys? Everybody kind of seeing the way that this one is going to work here before I talk to you about the issues we're going to have with it? Anybody else? Everybody seeing this or not? Just one. Okay. Well, what we got is this. I got stops motor that's going on right here. So you just got to be careful. What one is considered utilizing bits? I'll show you just a minute. Hang on a second, and I'll get to you. I got a bunch of different ways to do it here. The one thing that I want you to be careful is the retentive nature of this, because if you're in a subroutine, let's say you're in here and you've got memory in this subroutine, if you were to jump out of the subroutine, it doesn't necessarily kill the memory. When you reschedule this by hitting the selector switch, if it had memory before, there's a chance that it would have memory again. In this case, it wouldn't, because we're using the Q, which is global. So even if I had memory here, and then I unscheduled it by hitting the run jog, and I went to here, well, this would go off. And then when I rescheduled it and went back into here, even though it had memory, because it was off, it would immediately go off. But if for some reason in here I had an internal local bit, when I jump back into here, it would just take off from where it left off because it has memory. So you got to be careful with the retentive nature of this, okay? This one, run jog to schedule runner jog. So what's this got going? Here we go. These are function blocks. I got a jog function block and a run function block. Once again, I've got them interlocked. So if this one's true, this one's false, so this one's true, this is false. They can't be both. And inside of here, there's memory, and inside of here, there isn't. But notice what I'm doing here is I'm returning the motor and the motor. So I'm either getting the jog bit to run, or I'm getting the run bit. I can't get both because they're interlocked on their scheduling. And then what I do is I return that bit here, this bit or this bit to the motor. That way I'm only using the output here once. So does that answer your question here about how you could use these bits here in parallel? Because there's no way to get both of these true at the same time because they're interlocked on their scheduling. And then I only use output once. Good, Corey, good. Everybody else feel like they got this? Yes, no? All right, I'm seeing it, wonderful. Run jog programmed in function block. What's this? I got a jog and a run. Oh, they're unconditionally scheduled. So it's running both function blocks. It's running the jog and it's running the run at the same time. Notice I'm got motor, so I'm returning. I got the bit, so I'm either doing a run bit or a motor bit. So once again, I'm only using output once. That's good. That's good. And so I've got a choice here. What's my choice? So my choice is interlocked. My choice is interlocked. True, false, true, false. False, true, true, false, true. If I click choice, it's going to be true or false. So therefore, the ladder logic in here, if it writes choice as being true here, it must be false here, and it would be false here. So if I hit start, nothing happens here. Click the switch. So where now this choice becomes false, but the same input, choice becomes true. So when I hit start, I get memory, but this one doesn't work. So here I've unconditionally scheduled them, but I'm kind of using the output to the true, false, false, true interlock to write into each one of the function blocks true or false. Okay, so that's some ways to look at this. We did the EMS master control relay wired. Everybody seemed to have got that hooked up. You want to get good at that. so the master control relay wiring review is remember you hook up the master control relay and you source and sync the IO. You have the e-stop wired closed, okay? And so the key thing about that is when you do your logic, if you have a stop and you have a start and you have and you want some memory here. I'm just making a memory circuit, right? So if you wire your e-stop closed, then this automatically becomes true, because that's the way normally close works. So if you kill the MCR, then on your input module, where you have the closed push button, closed, you'd be getting a light on here automatically because it's closed. But if you kill the power to it, that light goes off, this goes off, and it would kill your memory. So that's another beauty about having your stop normally closed, because if the MCR dies, then it's going to bring down your system bit. This is pretty critical to understand to pass the class. Scale of 1 to 10, everybody's feeling good about this right here. The MCR, the normally closed, the system bit, how to kill it. Okay, if you don't know this, I encourage you to keep chugging through the labs, watching the videos, being sure you get it. We keep going over it, kind of every time, so that's good. So toggle switch is a single input. Remember, if you do a toggle switch into your input module here, or a selector switch into here, or I guess our toggle was this way. It was either this way or you could go this way. It was single pull, double throw. So you could go into, input 1 or input 2 with that toggle switch. So that's your options for a toggle switch. You could, have 2 rungs of logic, and you could have input 1 or input 2. And so depending on where that toggle switch is, it'd just be this true and that false, or this true and that false. Or if you just used input 1, what you would do is you just make one of these closed. And then therefore, if the switch is open or closed, the ladder logic is true or false or true. 2 different ways to do the toggle switch, single pull, double throw. Scale of 1 to 10, you understand both ways. I don't know if there's any benefits one way or the other. It just depends on what you want to accomplish. Some people were doing a little bit of both on this, okay? So that's good. All right. The run jog, once again, that was just your basic, run jog from 131, where the jog switch opened up memory or closed memory. So that either allowed memory or not allowed memory. And so you just had to kind of take that and make ladder logic out of it. And that's what I was talking about with the run jog. You just open and closing it, open. And then you just throw your extra, forward, reverse, your interlocks, because you want electrical interlocks. You just put all those fancy things in there. And then you scheduled it. And basically there was a couple different ways to do it. People took their function block, and here was the enable right here of their function block. And that certainly worked. If you had your function block, and this was my motor, and this was my motor, and this was forward, and this was reverse. That's what we were doing. We were coming up with a function block, forward and reverse. And so what some people did is they unconditionally scheduled it. You could use forward, reverse, forward, reverse. So depending on what, your forward, reverse, you unscheduled one and scheduled the other, scheduled one and unscheduled the other. So you couldn't have both the forward and the reverse working at the same time. And that's, this what I'm showing here. If for some reason you use the double here, then this was input 1 and this was input 2. So once again, by selecting it, you're either running forward or you're running reverse. Now, who did it this way? I think Oliver, did you do it this way? Did you conditionally schedule? Yeah, you conditionally scheduled your subroutines, and it's a way to do it. Yeah, I don't know. I don't know if anybody else conditionally scheduled their subroutines. This could be a single input in series with a run button. Yeah, there's different ways to do it. Versus like I was saying in the other one that your forward reverse switch, gets set into the function block based on your programming. And the example that is, and I know that a few people might have did it this way, but I'll just do it real quick. So if in my function block, let's just have this, and this might be on and out. Box this up, schedule it. I get on, out. Schedule it again. I get on, out. Okay, that's just me scheduling this function block. This goes to forward, this goes to reverse, let's say. Okay, so for the on button here, if I go like this, 1 PB, and I go like this, 1 PB, they're both unconditionally scheduled, right? So I hit run. This is true. This becomes true. This becomes true. Push the button. That becomes false. That becomes true. So therefore, this goes off. This goes on. So you just use you got like a little bit of a scheduling mechanism to inside of the function block. You're either writing that contact as true or false. They're interlocked. You can do both. It's either on or it's off. The same logic is used twice. And this tag right here and this tag right here don't see each other. They're internal. They do not know what each one is doing. But this push button here, which is I1 and I1, these are global. And when you push them, one becomes true and one becomes false and one becomes false and one true because there's only one push button. Scale of 1 to 10, how are we feeling about that explanation there, especially with the local and global? Corey, I think that's how you did yours finally at the end. Anybody else doing it this way? I can't remember what you guys were doing. I think a lot of people were kind of trying to get some scheduling kind of going like that. All right. So the quiz was just math, I think, and everybody did pretty good with that. So I'm not going to necessarily go over that too much. I can go over in class if you want to. I put here in class worksheets are not a substitute for your knowledge. And that's coming up because we have the crosstalk between the Siemens and the Allen Bradley that I want you to be sure that you understand before you get there. Otherwise, it's going to be a really long day for you. But yeah, as far as the math goes, people got that. It maybe your in-class worksheet helped just because it was straight out. But otherwise, the stuff that we're going over, just try and understand as much of it as you can. All right, so we're moving on to this week's topics, which are scheduling. We'll just talk a little bit more about scheduling. We're not doing a lot of scheduling right now. If you take the advanced PLC class, PLC2, can we go over some of the Boolean math? Why don't you stick around afterwards and I can go over it with you, because the quiz scores were like high 20s, high 30s, 27s, like that. That all right? Just stick around and I'll knock down some of the Boolean math if you would like to. I can pull that out. Okay, thank you. So we're talking about scheduling, routines, tags, timers, and counters. All right. So like I said, we're not doing a lot of scheduling. We're going to do scheduling a lot in the next class. But when you start a project, you guys have started a project, and this is for Allen Bradley. It contains all the programming configuration information with your tags, tasks, everything like that is going to be for your CPU. You can do one project at a time. The Siemens project is what you guys have been doing, is right here, the Siemens project view. And if I go to my Siemens right here, this is my, I can go back between the two, and it's the lower left down right here. If I click portal view right here, that'll bring me to this page where I can add a device. If I wanted to add an HMI, I can add it on here, controllers and different devices. But then the project view is over here. and then our organizers here on the left. And I feel like we're probably starting to get through the organizer pretty well about where the tags are, show all tags. And once again, once they're up, you get a little tab down here, and it's really easy to go between the items once the tabs are up here, okay? So you're getting better and better at that. The Allen Bradley looks similar. There's a tree over here, an organizer. And once again, it's just going to show you your PLC, all your tags and all the information. And when you work with PLCs, you're going to get really good, you know, it navigating through these. And here's the Siemens organizer, you know, once again, your PLC, your main, your function blocks, your functions, your data blocks, your tags, everything is just going to be, you know, kind of over here. Right now, the main ones we've been using are your main, your function block if you wrote one, and schedule it with a data block, and then your PLC tags. You know, that's kind of what we've been, you know, using and navigating on the software. So Allen Bradley has three levels of scheduling: task, programs, and routines. Siemens has 2 levels of scheduling. That is your program blocks and your routines. So that's where we've been at right now. Our program blocks are our main OBs. So your OBs are your main, is the first level. And then your functions blocks and your functions are your second. You can drag or schedule these function blocks into, for example, your main, and that's what I've done here. That's the second level of scheduling. This test function block does not run unless it's scheduled, okay? And once again, here I'm showing conditional scheduling. So this one would be, you know, depending on if it's open or closed, this would be scheduled and unscheduled, or click the switch, scheduled, unscheduled. But if you want to unconditionally schedule them, you can just delete this, and now they're going to be unconditionally scheduled, okay? And that's the way to organize your program. Program blocks are the first level of scheduling within a task, okay? And the key thing here is that these tasks are continuous. We talk about continuous tasks versus periodic tasks, and continuous blocks versus continuous blocks, okay? The Siemens continuous task is called the main OB. So if I come right here, and I've got the main OB right here, what it does is it runs, let's say we put ladder logic in here, just like it did for the Allen Bradley. It would read the ladder logic like a book, left to right, left to right, left to right, left to right. It read this whole book, then move on to the next chapter or down here if it want to, left to right, and then it would just jump back at the top, and it would just keep reading left to right, left to right, left to right, okay? If you put subroutines in here, and let's say this had like 500 lines of ladder logic in it right here. Well, it would start reading the book. It would come here and it would come to test, and then it would jump into test. It would read those 500 lines of ladder logic. Then it would jump out of test and jump down here, and then jump into this second instance of test and read these 500 lines of ladder logic, and then jump back out. And then if there was nothing else to read, it would come back to the top, and it would start reading the book again, or it would start your scan again. And whether your ladder logic is in a subroutine, or whether your ladder logic is just in your main here, yeah, go ahead. You can
So
ask.
let's say in test 1, there's a timer,
Yes.
and it reads the 500 codes. Let's say it finishes reading the 500 lines before the timer goes off, and then it hops to test 2. But like, you know, the test 1 timer is still counting. If the timer is done while it's still reading test 2, does it update? Does it go back up and update it, or does it wait for test 2 to be done before it updates the timer in test 1?
No, I think what you're asking is, it's just going to be looking at that timer. It's not going to wait for that timer to get done to jump back out and then start reading this book. It's just going to note the value of that timer, and then note the value of the timer. Then when it starts over again and it comes back into here, it will note that, hey, that timer has increased a little bit, and then it'll just jump back out. That's what you're asking, correct?
Yeah, but then what if it finishes? Will it update even though it's reading the second test?
It will. And so what we've got going, and the difference of these controllers, especially because of the scheduling issues, on the Allen Bradley, we learned that you check the inputs, you solve the ladder logic, and then you update the outputs, and then you start again, keep running around just like that. Inputs, ladder, outputs, inputs, ladder, outputs. And the timers and everything are in the ladder logic. And everything would be updated right here at the outputs, and then it would start again. Okay. Now in the these third generation PLCs, there's different asynchronous scans going on. The ladder scan is its own scan, and the IO scan is its own scan, and the timer scan can be its own scan. So here what we're used to, or here what you might get is that these things are, you know, running at different speeds, different, and later on we'll learn that you need to sync these scans up so that they do read and update like what you want them to, okay? And that's a little bit more of an advanced topic for the next class, but we will talk about in a minute about the timer scans, okay, about how they update, because you can get an instantaneous read of the timer on these in the middle of the scan, okay? And so hopefully I'm answering your question a little bit, but for the sake of the way that it's going to work, because the scan is so fast, it's almost going to work like this: input, ladder, output, input, ladder, output. Even if the ladder's here, by the time it solves that timer and updates the output to it and everything like that, it would have blown back, you know, through it to get there really fast. But like I said, in the next PLC class, you learned about mapping and how to sync your scans up a little bit. But that's a really kind of an advanced topic that we're not going to totally dive into on this one. Hopefully that kind of answers your question enough to keep going. So once again, we have these continuous blocks where, you know, it reads the program and ladder logic, next program, next one, and then it just jumps back up. So, you know, the scheduling can get, you know, pretty complicated. I'm going to show you a little bit here in just a minute, although we're not going to necessarily use it so much in this class, but you'll see it out there, you know, once you get into PLCs a little bit. Periodic blocks are blocks that get interrupted. So we have the continuous tasks that are running. And so you wrote a program like a stamp, you know, you hit start, the motor starter came on, then you hit another button and the cylinder went back and forth 3 times, and then you hit it again and the light came on, and it did like 3 times. You guys did that capstone project for the SLIC 500. And basically it was just running one line of code, and it had a state manager, and it processed all that code on a continuous task, okay? But now there's periodic tasks here. Now a periodic task, if you call one, it will interrupt the continuous task. So the processor will stop running the continuous task, and it will run the periodic task for however amount of time you want, and then it'll keep running the continuous task. And it'll do the periodic task, and it'll jump right in. A lot of times these periodic tasks are quick hitters, you know, a few milliseconds it'll run a periodic task, and then it will jump back into the continuous task. Another one would be an event-driven task where, you know, you hit a limit switch or something like that. And what it does is it would stop the continuous tasks. It would run that event-driven task, and then it would come back, and then it would just keep running the stamping cycles off like you want to go again, okay? So when you get into this, it's going to be, you know, a little bit more complicated. So what do we got here? We want to create a program to run a washing machine. Let me see. Start by creating the different types of programs and appropriate scheduling. Okay. So if I was going to be, you know, scheduling this out, you know, right away, let me just delete some of this. I would come here, and it wants me to come here, and it wants me to add a new block. Okay. And the first one is going to be called map inputs. Now, how do I want to do this? I want to program it in ladder logic. That's fine. I don't want it to be a subroutine. No, I want this the following types of programs. No, I want it to be an organizational block. So this could be a program cycle, startup type. These are all the different. I talked about an interrupt here, or timed interrupt. These are some of the things that it would do. But this is just going to be a program cycle, and I'll click OK and let it go here. And you notice now I've got another OB here. And so the way that this is going to work, it'll run the main OB, all the ladder logic in it, anything that's scheduled in there, and then it will come out and read the map inputs, any ladder logic, anything that's scheduled in there, and then it will just jump back to the main map. These are all continuous. It'll just keep going, all right? I want a false one. So program blocks, new block, it wants false. Let's see what I want, false. That's gonna be an OB. And once again, maybe I want a, so time delay startup. What I have here, global washing. Let me see if I want to do a kind of a startup. I could do a startup. Oh, where is it? Is it here? Yeah, beautiful. I knew it was there. We'll run with it. So there you go. We'll make it a diagnostic error. So this fault, once again, it's going to be running, then run this and run this and run this and run this and run this. But maybe this fault it's only looking maybe for one thing, maybe to stop the controller if there's a fault or something like that. Let's do a global. One more. Add a new block. And let's see, I'll do this as what global OB. I'll call this a startup block. Okay. And so it comes in once again, this global is going to have some ladder logic and I could go in there. You know, I don't have anything in there right now, but you know, it would have ladder logic in it. It's just going to run this one, this one, this one, this one. So the OB100, because it's a startup block, every time you switch the processor on from start to stop or download, so when you start up the first time, the global, whatever's in there, runs one time. You run a scan one time. You'll do a scan, and then it will never run this global scan again unless it gets started and stopped again. So you know, there's different types of items that you're going to add here. It wants one new block. I think it wants washing machine. Washing machine. It's just a program cycle. It's an OB. Okay, and this might have all the ladder logic and everything in it to run a washing machine. But you know, each one of these could have different priorities. They could be continuous. They could be an interrupt to where, you know, they only run during the interrupt or anything like that. And so be aware that when you go out there, you're going to start seeing different types of, oh, I was supposed to make that continuous. Oh, an error interrupt. Good. Okay. Yeah. So I was supposed to make these different ones. So these are the continuous ones. The map inputs and the washing machine are the continuous. This only runs once, and this only runs when there's an error interrupt. Okay. So here's a few examples real quick. So fill a tank to its maximum level, open a drain valve, collect parameters. This is like what you guys did. Turn the starter on, stamp 3 times, turn a light on, stamp some more times, turn a light on. These are just all continuous tasks. That's all we've been doing up to this point. It's just continuous tasks. We've been programming ladder logic. And let's say we had that ladder logic and it was running, but we threw in this right here. Read the thickness of paper every 20 milliseconds. So every 20 milliseconds, all this stamping and tank filling and cylinders and starters and everything, it would stop. It would not run that. Every 20 seconds, it would read the thickness. And then it would go back and then just keep running all the stamping and draining and filling and everything like that. And then 20 seconds, it would stop it again. And then it would just, so this reading this paper would be a periodic test. An event-driven task would be capture data immediately after receiving production, load the data into the station. So you got this event-driven task, and it was running all this continuous task of stamping and filling and draining and motors. It would stop it, and then it would load up the new production data. And then as soon as that was done, it would jump right back to your program and just keep running the program that you thought that it was always running. Because it's probably going to be so fast that you might not even notice it. So some of these tasks that you program need to be called, and they could be called continuously, they could be called periodically, or with event driven. So we have once again, the main program. That's kind of what we've been doing. We've been working in the main OB. We've been doing, you know, our routines, and our routines could be programmed in ladder logic. You guys were messing around this time with your routines. I think some people were going difference between FBD or whatever, but routines could be programmed FBD, ladder logic, structured test, sequential function chart. You got to pick one though. You can mix them. You can mix the routines, but within a routine, you can't do both. You can't do function chart and ladder logic within the same routine. Okay. but you can schedule routines with different languages. So the main routine is configured to execute first. A subroutine is called by that routine, and then there's going to be a fault routine. Usually you have one fault routine that gets called. Do you want to fault the CPU? So we got another one here. We're going to create some subroutines, okay? And so I come here and I go to my program blocks, add new block, and I'm going to make a subroutine, and I'm going to do AA fault, and it's going to be a function block. We can program it in ladder. Okay. I'm going to add new block. It wants BA cycle select, and it's going to be a function block, and we could program this one in SCL. That's fine. And then I'll do one more block. It wants BB temp selection, and it's going to be a function block. And this one could be programmed in FBD. Okay. So I've got these different, you can imagine what's in the cycle select. You know, you're going to, permanent press, quick wash. I don't know, whatever's on a washer. Your temp select, hot, warm, cold, cycle starts, inlet valves, outlet pumps. They were showing, on my little sheet here, all the things how you might organize this for a washing machine. The program that I'm going to put down here is washing machine right here. And so if I pull up washing machine, I'll close this up real quick. I might start with, this here. Boom. Scheduled. Okay. And then I can either put it here or I can, add it here. The next one would be cycle select. I'll throw it here. It's giving me a data block because I'm throwing this, and I'll do one more here. Temp selection. Oh, give it to me. Where'd it go? Right there. Temp selection. Sure. What's my data block? Sure. Yeah. And so you could expect, once again, if I clicked in here to temp selection and I wanted to look in there, there'd be some ladder logic with some sensors that are picking up, the temperature selection and greater thans and less thans and triggering inlet valves or something like that. But you're going to get, pretty busy here. But if I go to washing machine, once again, these are going to be all unconditionally scheduled. And depending on what you got in here, what kind of internal tags, you're using internal and global, they might populate here just to keep everything organized. So once again, then it runs, faults is only going to run when it's false. Global only runs once. It runs everything in main. It runs everything in here. It runs everything in washing machine, which happens to be everything in here and everything in here and everything in here. And then it jumps back out and it runs main again. Everything in there, everything in there, everything in machine, which is in here and everything in there. And it jumps out. It runs all the ladder logic in here. And it jumps out and runs all the ladder logic in here. And it jumps out. It starts again. It just keeps reading this book, and it reads it, very quickly through the continuous cycles. If for some reason we get an interruptible situation like a fault, it will stop reading the map inputs, the washing machine. It'll read the interruptible, and then boom, it'll jump right back in, and it'll keep reading the book. Mains, map inputs, washing, all the subs, all the ladder logic, everything in it. This concept of scheduling, basically, just a rough understanding of it, scale of 1 to 10, you kind of see in it how it works. Yeah, and so you'll see, like I said, when you look in the Allen Bradley program, you're going to see. You can see some ladder logic in the main, but not much. All you're going to see is JSR, jump to subroutine, JSR, jump to subroutine, JSR, jump to subroutine. And then if you really want to know what's going on with your washing machine, you're going to have to jump into that subroutine, which if that's the valves subroutine or that's the temperature subroutine, jump into there. And then you're going to see all kinds of ladder logic, and you can kind of keep track of what's going on. So there's where I've got this, of calling the subroutines. All right. A couple things. Tag-based addressing. Siemens uses tag-based addressing structure. We've been doing the tags to give them a name that seems like it makes sense. You can name your tags Dorito, but motor starter 1 or motor starter or something like that, or stop, start. That's probably going to help you. And then we went through here of using the PLC tags, of creating your tags ahead of time. Everybody doing good with this? Creating your tags ahead of time or modifying your tags here. and then using them into your program. These are your global tags, okay? And if you're doing, you know, your local tags, if you're doing locally, that, you know, in here where you would put, you know, local tags in here, and then when they get scheduled, that's where you're going to see your local tags internal to the function block. Might have to do an update block call if I added them there. Tag scope, that's what we were talking about, that, you know, your controller scope tags your sensor one, temp one, you know, you're going to have a sensor hooked into there, and you're going to have a temperature sensor in there. And these controller scope tags are going to be IQs and M's. You can use it wherever. Okay. That was your global tags versus your local tags. You know, sensor one globally could cause something to happen in program A and program B, but this tag one and this tag one, they don't see each other. You know, just because this tag one is true here doesn't mean the tag one is true here. You can have identical tag names within your subroutines, but your global tags, you're really only going to have, you know, one temperature sensor. You only have one I1 or one Q1 or one I2. You can use I2 as much as you want, you know, to open and close contacts, but there's really only going to be one sensor. So that's my difference between my local and my global. Alias, that's what I was talking about. You want a name like a fan motor. That's a good name, fan motor. And that's going to be associated with your base data. Here's Allen Bradley. Locus means on your local rack, slot 2, output bit 5 is your fan motor. Well, sometimes that's too hard to remember. Maybe you just want to turn on the fan motor. And so you can give it a name and it will tell you what it is. Ours does, you know, similar here. Let me throw something in here. You know, if I put it here, no, I don't like that. You know, I'll just put it in. It'll tell me the name of the tag and it will tell me the address as well. So you get both. You know, the alias is light, and it's alias for the base data of Q0.1. And you put the output module, you'd think that you would see, you know, something hooked in there at that. PLC data types. The data types can be base tag or Boolean, which is, we've been doing a lot with it. It's digital, discrete, on or off. You know, things are on or one. We talked about SINT because of the way that some of the IO was organized on here. Don't see this as much. A lot of times what you'll see is an integer or a word, or we call this a register. 0111, 011, 0111. That's, you know, 16. A double integer is 32. And then a real number is floating point, where you can get, you know, 17.25. You'll have decimals if you want. Okay. Just depends on what kind of data you want. A Boolean is 0 or 1. 8 bits, 0, 1, on or off. SINT 8 bits. So you got 0, 1, 1, 1, whatever binary you can get with 1, 1, 1, 1, 1. 1, 1 is somewhere up to 128. Integer, you can have 16, 0 to 15. If you get 1, 1, 1, 1, 1, 1 all the way up there, you get up to 32,767 to negative 32,767. That's the binary equivalent of this. A double a double word, 2 to the 31st, you get 2,147,000,000 possibilities. So as controllers got more advanced, the registers got a little more advanced, gives you a little bit more room for data. And so just to look at this SINTN real quick once again, it would be 1, 1, 1, 1, 1, 1. This is the ones, this is the twos, this is the fours, this is the eights, this is the 16s, this is the 32s, this is the 64s. 1, 2, 3, 4, 5, 6, 7, and this is the sign bit. So 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 127. Okay. If you kept going with 1, 1, 1, 1, 1, 1, 1 for 32-bit, you got plus 128 plus 256 plus 512 plus 1024, etc. You add it all up, you get 2,147,438,7. So that's just the way that the data is organized and how you can look at it in the data table. All right. Before we start timers, everybody feel okay with you know, your bit values here? We've been using some ints. We've been using a lot of ints here. We haven't been using double integers that much. One thing was this at 500 just used ints. These third generation are using your double words, so you get, you know, much bigger values here. Like you can have your counter now, your timer now go up to 2,147,000,000 instead of just 32,767. All right. All right, timer types. We have, and I'm going to go through this. And we're rolling. I'm gonna give everybody just a couple minutes here. You guys need. There's not much. Yeah. You guys want 5 minutes? Or you want to keep going? 5 minutes. Keep going. Keep going. All right, we'll keep going. Yeah. So part of this is just you kind of got to get in and program the timers and see how they work. And so it's going to be the same as the Allen Bradley. You got TONs, TOFs. You have these pulse timers, which are a little bit different. These are added from the menu on the left, or you can, you know, pull them in like this. And that is what is shown. You can bring this in right here, and then you can double click it and you can start typing TON. Boom, there's a TON right there. And when I put it in, it says, do I want a data block? Yeah, I do. Isn't that funny? It brings a data block in because it has to remember, you know, where it's at. So if I come in my system blocks right here, program resources, there's my timer. And if I go in there, it shows my PT, my ET, my and my Q. These are the equivalent to my preset and my accumulation and my done bit and all that kind of stuff that we did for the Allen Bradley. It's keeping track of them here. So when you put that timer in, it's going to come in with a data block, and it looks kind of like a SUG 500. It's a rectangle. It's a timer that comes in, and it'll go in great. Okay. Siemens timers. You can program as FBD. They got an FBD look to them, and you can program them as FBD if you want. But you know, they look, like I said, they're kind of rectangular. They kind of look like Allen Bradley's did. They came in. You could be programmed it as a coil. Don't do that, because if you do it as a coil, you'll need to add a data block. Whereas if you put it in just like I did, then it will ask you right away, you know, I'm creating a data block for you, because you want the data block because you need to know what's going on with it. Okay. The way that it works is my IN is Boolean, which means is the type, you know, is it true or not to the timer? It's kind of like the enablement, the .en on the other one. Yes or no, it's on. Preset time, that's a word. So you're going to put the preset in of like 200 seconds, 400 seconds, 2 seconds, whatever. It's a word because it's not off or on. It's a value. It's a number. The amount of time that is lapsed. ET, that's a word. That's like your accumulation. And then your Q is Boolean. Is this done or not? Okay, that's Q. Is it done or not? All right. Here's what it says. IN makes it true. It's like the enable. PT is preset in milliseconds. You want 2 seconds. Type in 2000 right here. Boom, you get 2 seconds. ET is accumulation, like the ACC bit. So accumulation bit. Q is like the done bit right there. Okay. So I got a little thing in there that says Siemens timer handout. All right. And if you read this, it goes through and it says that the timers are part of their own scan. You can get the latest time data, essentially an immediate read of the timer whenever you want. If you look into the queue, okay. However, you desire to have a consistent value throughout, then please place your instructions prior to all other instructions that need the values. Use tags on the Q and ET, because if you access the Q and you access the ET of the timer while it's timing, an instantaneous read of it in the middle of a scan, it will reset the timer. Okay. And so that's a little bit different, that you might want, you know, those to work. So I've got just a couple of examples here, and then we'll be done. You'll have to just figure it out in the lab. Here we go. Blinking light using 2 timers. I got timer, timer, Q. So here's the timer 0, Q. So that's like the done bit. Done. Starts this timer. There's the Q, timer 1 Q. Timer 1 Q opens, which opens, closes. Time, open, open, closed. Time. So this is a cascading timer right here using the dot Q. That I said the dot Q is like the done bit. This is like the timer dot done, and this is like this timer's dot done. So first of all, just these 2 timers cascading. Does it make sense that this Q is like the done bit, and this Q is like this one's done bit, that they just cascade, scale of 1 to 10, that one timer is going to start the next timer? This just looks a little bit different. So using the done bit, it just got dot Q. Anybody else? Timer, dot Q. Dot Q. This timer gets done, there's the dot Q. All right. So if this is the blink timer, this is just going to close, open, because this times out, opens, resets, closes, times out, opens, times, resets. So this is gonna work. All right. What I like about this is this light is on its own rung. I like having the output on its own rung. Don't put the output off the end of the timer. You'll get in trouble. I like that you can control it. If you somehow need to bypass it, parallel stuff like that, then you're in business on this light. Okay. If you were to take this rung right here, because it's timer.q, and put it, down at the bottom here or between these, this wouldn't work, because when this thing reached in and grabbed this .q, it's looking for the .q, it would automatically reset this timer. So this would only open for the amount of time it took this to reset. So very short amount of time. And you're like, that's really weird. Well, you'd have to program some of this stuff and see it to believe that this is working like what you want to, okay? And that's why it says you want to think about using an M-bit. So here's another one, ready? This is true. So this times out, Q, light comes on. Light starts the blink timer. It gets done. Turn on the process bit. Open. Off, on. Times. Off, on. So this is a cascading timer as well. Notice I did not use the .q here, okay? Because I don't want to instantaneously read the timer reset by accident, depending on my ladder logic. I put stuff here. What I don't like is the light's no longer on its own rung. Here, I like the light on its own rung in case I needed to go around it or, bypass it or do something else with this light. Now the light's here, and I'm like at the mercy of all this logic in this timer here to turn this light on. So that's what I don't like on it. This process bit, I do like this. I'm no longer using the .q to open this up. I'm having the .q turn on the bit. It's the bit that is resetting this timer. And I'll have you work through the lab to see how that works, all right? Blinking lights, how about this? So I got timer doing a bit. The bit starts the next timer. That bit opens up this timer. Bit, timer. It cascades like this. Open, close, open, close, open, like that. I like this. And the light is on its own run. And there's logic here. The bits are turning off and on. They're not at the mercy of that. So this is probably the best practice to blink a light. Here, we learned everything can go in series, right? Well, if it's done, this turns on the light turns on this timer, it gets done, comes back, opens this up, timer, this works. It probably works, but you're like, what if I want to do something with this light by itself? Well, you're not. It's trapped between timers and you can't parallel around it or anything like that. That's why I like to have the light or whatever the item is on its own rung. So this is probably not a good idea. All right. Next, fine, I'll get near the end. Counters. So once again, the counters will go in pretty much like a counter. R is the reset. It's need to reset. You make this true, it resets. Preset's a word. You want to put 8 in there. It'll count, 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 count. When the count value, which is a word, or the accumulation reaches the preset, it becomes done. And once again, I'll probably have you put a bit out here. Instead of using the counter.q, I'll have you make a bit called counter done bit. And then you can use that to do stuff. So I'm going to stick around and talk about some Boolean math, I think. But a lot of this is just getting into the lab and using the timers and counters. Take a look at the last one, because what it is that crosstalk activity, and that's going to be a bit of a doozy. You'll work with somebody on it, and you want to have it planned out, or you won't even begin to get it done. You won't even get to first base. So take a look at that timer counter. You'll be working with somebody. Okay. Now that was, once again, a crash course. I think we're doing a good job of kind of getting through the labs. You got to get through, do your timer counter lab and see how it goes. What questions do you have for me? Hang on, something happened here. Anybody? This thing is really working weird. All right. If you don't have any questions, you'll come in. Where is the crosstalk stuff you want us to take a look at? Wow, this thing is freaked out. Hang on. I'm going to share this again. So I'm sharing. Hopefully you can see this again. Here's the lab. Let's see. Take a look at this. Grades should be pretty updated. I'll probably get through some more tomorrow if I don't have it. The crosstalk stuff is there's up down counters, timer counter. This is going to be right here, a timer counter, where you're going to have a slick 500 will blink, or whichever one it says the master will blink a light, and then it will cause the next Siemens to blink a light that will then cause the slick 500 to blink a light. People should have turned a light on the master. So the Siemens is the master. The slick 500 is the slave for this timer counter one. And we've got lecture notes that we went over about how to interlock two different controllers using interposing relays. Does that answer your question? You guys are still here. Okay, you still there? Why is my thing not so happy? Okay, so that's, you don't have this part F timer counter in your packet. Okay, we can print this off then out of the thing, off of the page 12 of 14. Yeah, that's 14. Should be in there. We can look at it. Otherwise, you can print it off of the D2L when you get to class. Might want to do that just to be sure. I don't know what's going on with yours, if something got scrambled or not. All right, what else? It's on the D2L here. You need to take a look at it, compare. And we've got lecture notes on, we went over how to do this cascading timer counter stuff. So take a look at it. What else? Good questions. Man, this is really weird. Collapse video view. On my D2L, there's quizzes posted the same. Let me look. So if I come to quizzes, it says quiz 10 function blocks should be open right now. Is that what you're asking about? I see quiz 10 function blocks is what's open. So I don't know what you're seeing on your. Okay, one, never mind. Wonderful. All right, what else you got? Okay. So you have the quiz, and once again, you'll get into the lab. You'll see the time. The timers are just going to go pretty fast. You're just going to got to work through it and just see how they work. And you're going to see just like Alan Bradley. So that's why I'm not killing it on this. But then that last one, that the cascading timer counters between the two controllers, just plan ahead a little bit. And hopefully, it'll make sense for you. All right, I'm here to answer what other questions you got, or you can go take your quiz. This is really weird. Nobody's here?